Yeah. Good afternoon, everyone. Today's colloquium speaker is Sir Thomas Kibble, a British theoretical physicist and senior research investigator at the Imperial College London. His research interests are in particle physics, as we know, of course, and its interface to cosmology. He has worked on mechanisms of symmetry breaking, phase transitions, and topological defects that can arise in these phase transitions. His paper on cosmic strings actually introduced the phenomenon to modern cosmology. But Sir Kibble is, of course, most noted for his co-discovery of the symmetry-breaking Higgs-Kibble mechanism, together with Guralnik and Hagen. He is member of countless physical societies, such as the Royal Society, and was awarded many prestigious prizes, like the Albert Einstein Medal and the Dirac Medal. Moreover, recently he became knighted at the 2014 Queen's birthday, together with Sir Viddy. I'm sure he has a lot of interesting things to say about the history of symmetry breaking. Please go ahead.
Well, I'm very pleased to have this opportunity to come to CERN and talk about the history of this subject. This is really a historical talk from my own particular perspective as a member of the Imperial College group about how the electroweak theory evolved. And of course, that includes the development of the Higgs mechanism, which has recently resulted in the discovery of the Higgs boson. These are the things, I don't think I'll read out that list, but this is essentially the list of things I will talk about. Let me start by saying something about Imperial College when we started. I've always believed that it was a stroke of enormous good fortune that I was able to join the Imperial College Theoretical Physics Group in 1959, less than 3 years after it had been founded by Abdus Salam. The same year that I joined, Abdus became the youngest fellow of the Royal Society at the astonishingly early age of 33. It was a wonderful place for a young theoretical physicist to be. It was a very exciting group. There were lots of visitors. Salam, of course, already had a tremendous international reputation because of his work on renormalization theory. And he attracted huge numbers of visitors. Murray Gell-Mann, Stanley Mandelstam, Stephen Weinberg, Ken Johnson, Art Rosenfeld, lots of others. So what were we interested in? Well, of course, after the great success of quantum electrodynamics, which was the real success story of the post-war period, the obvious next question was, could we find equally good theories of the other interactions? And perhaps even better, a unified theory of all of them, which is something we're still looking for. And people started to ask, could these also be gauge theories that describe the other interactions? Most of the interest initially was in strong interactions. That seemed the obvious next step. And of course, there were candidate field theories around, like Yukawa's meson theory, but it was very difficult to make progress because nobody could do any calculation. The only way of calculating we knew was perturbation theory, and you can't do perturbation theory with a coupling constant of order 1. And for that reason, a lot of people had lost faith in field theory. S-matrix theory was all the rage. We were talking about dispersion relations and Reggie poles and all sorts of things. There were a few places, including Imperial College, where field theory was still very much in the forefront of our ideas. And people started to wonder whether weak interactions were not a better bet than strong interactions, for the obvious reason that if you have a theory of weak interactions, you can actually do some calculations with it. Now, the other thing that was happening at the same time was on the experimental side. At the end of the war, we had a handful of elementary particles. Within a decade and a half or so, we had hundreds. People had found lots and lots. And so we had to try and make sense of that. And that was done largely through finding symmetries. First of all, there was the isospin symmetry, which was invented by Werner Heisenberg in the 1930s. I mean, he, of course, started from the observation that protons and neutrons are very, very similar. They have the same strong interactions, more or less. They have nearly the same mass, they have the same spin, and so on. And so maybe these are two states of the same underlying particle, the nucleon. And and moreover, he hypothesized that there is a symmetry between them, which is in which you can rotate the proton into the neutron, or vice versa. And that's why it's isospin. It's not, of course, anything to do with real spin. And then we had the eightfold way, which was a realization that you could make larger patterns, two-dimensional patterns of the particles into octets and decuplets, and describe them by an SU3 symmetry rather than SU2 symmetry. And that was invented or discovered by Murray Gell-Mann and independently by Yuval Ne'eman, who was a student of Salam's at the time. And that is now seen as a symmetry of the three lightest quarks, whereas, of course, isospin is the symmetry of the two lightest quarks. But the eightfold way clearly is broken. They're both broken. The isospin is broken by electromagnetism, and the SU3 symmetry is broken much more severely by whatever gives different masses to the quarks of different generations. So there's are approximate broken symmetries, and people started to ask, could that be spontaneous symmetry break? Actually, it isn't in this case, as far as we know, but spontaneous symmetry breaking started to be talked about. The other thing that was a very important ingredient to feed into people's ideas at the time was, of course, gauge theory, and in particular, the theory of Yang and Mills, which was the first gauge theory beyond quantum electrodynamics. It was a gauge theory, an SU2 gauge theory, in which the isospin group is gauged. And the same theory was actually written down by a student of Salam's, Ronald Shaw, in 1964 also, 1954 also. But he never published it except as a Cambridge University PhD thesis. And ultimately that has not proved to be the correct theory of strong interactions, but it was nevertheless the foundation for all later gauge theories. And it's very interesting that, as I said, at the beginning of the 60s, field theory was really out of fashion. S-matrix theory was all the rage. And yet, if we look back now and ask what was the greatest achievement of the 1960s, nobody would mention anything other than gauge theories, really, I believe. Because isospin is an approximate symmetry, then obviously if this was a good theory of strong interactions, which it isn't in the end, then the symmetry would have to be broken. But the trouble with that is that if you just add a mass in to a gauge theory, you spoil its nice properties. That was already well known. So people started to ask, could the symmetry be spontaneously broken? If you just add a mass, you get a theory which is very obviously not renormalizable and becomes nonsensical at even quite modest energies. So, unification was one of the things that people were looking for, and particularly after it was discovered that the weak interactions could be understood as being mediated by spin 1 particles, the W plus and W minus. Because the weak interactions proceeded through a V minus A interaction, not ST or P, they could be understood as due to the exchange of spin 1 bosons. And for that reason, people started to think that there might be a gauge theory of weak interactions. And the first suggestion of such a gauge theory, as far as I know, came from Julian Schwinger in 1957. And he actually suggested there might be a unified theory in which the W plus, the W minus, and the photon would somehow be unified with some sort of symmetry between them. But obviously, it had to be a very broken symmetry because in order to understand the short range of the weak interactions, you have to assume that the W plus and W minus are very heavy, like 100 times the proton mass. And also, of course, the weak interactions violate parity, which the electromagnetic interactions don't. So how can you have a unification of these? That was a big problem. Well, the problem of parity was solved by Shelley Glashow in 1961, who proposed a model with an extended symmetry group, SU2 cross Z cross U1, and a fourth gauge boson, Z0, showing that the parity problem could be solved by a mixing between the two neutral gauge bosons. So you can have a theory in which there is a symmetry that involves the W plus, the W minus, Z0, and the photon is the only one that has a parity-conserving interaction. Salam and his long-term collaborator, John Ward, actually wrote down a very similar theory, also based on SU2 cross U1, apparently unaware of Glashow's work, 3 years later. Salam was always convinced that a unified theory would have to be a gauge theory. But there was still the problem in all these models of giving masses to the weak gauge bosons, the W and Z. They just had to be inserted by hand, and that gave a nonsensical theory. So the big question was, could this somehow be spontaneous symmetry breaking? That idea was really first mooted in the context of particle physics, I believe, by Yoshihiro Nambu in 1960, by analogy with the way in which the plasmon acquires mass in superconductivity. He suggested a similar mechanism could give mass to elementary particles. And he and Ionello proposed a specific model to do that. This is not, of course, a gauge theory. It has a 4 fermion interaction in which the phase symmetry is exact, but the chiral symmetry involving a gamma 5 is spontaneously broken because the psi bar psi acquires a non-zero expectation value, and that gives a mass to the psi field. But an important feature of this is the fact that it has a massless pseudoscalar, which they identified with the pion. That was a bit problematic because the pion, of course, is not massless, and they had to assume that somehow the symmetry wasn't quite exact even before the spontaneous symmetry breaking. Spontaneous symmetry breaking is a very familiar feature of many branches of particle physics, where the ground state or the vacuum state doesn't share the symmetries of the underlying theory. The simplest example is crystallization. It's often associated with a phase transition where you have a high temperature symmetric phase and a low temperature phase in which the symmetry is broken. In crystallization, if you take a circular bowl of water, it looks the same from every direction, has perfect rotational symmetry, but when it freezes, the ice crystals form in particular directions and break the symmetry spontaneously. Spontaneously in the sense that you can't predict which directions they will be unless you know something about defects in the bowl or something else. And the same thing occurs with a ferromagnet. When it cools through the Curie point, it can magnetize in this direction or that direction. And in a superconductor, the gauge symmetry is actually broken, although that was a contentious issue for a long time. Sorry, something's gone wrong with this. It's better. But there was a big problem with this idea, applying it to the particle physics context, and that problem was the Goldstone theorem. And that, in a sense, is the central feature of what I want to talk about. Let me remind you about the Nambu-Goldstone bosons. In many cases, spontaneous symmetry breaking of a continuous symmetry leads to the appearance of massless spin-zero bosons. The simplest example of that is the Goldstone model, which is simply a model with a complex scalar field with this sort of potential, the sombrero potential. The point is it has a maximum at phi equals 0. It's perfectly symmetric under phase rotations, but the maximum at phi equals 0 means that the lowest energy state has a fixed magnitude of phi, it lies somewhere around this circle. So in the vacuum, the symmetry is broken. The vacuum expectation value has a fixed magnitude, but an arbitrary phase. This is a degenerate vacuum. And in that situation, it's easy to see that there are massless particles. Suppose we choose, for example, to sit here, where choose phi to be 0, to be real and expand phi as a expectation value plus real and imaginary parts, then a very simple calculation will tell you that there is a mass term for the phi 1, but no mass term for phi 2. And the reason for that is perfectly obvious. The potential has a curvature which defines the mass of phi 1 in the radial direction, but it's flat in the transverse direction, so phi 2 is massless. So you have these particular masses. And that was believed to be inevitable in a relativistic theory. And indeed, this is the content of the Goldstone theorem. When Stephen Weinberg spent a sabbatical year at Imperial, he came in 1961 to 62, he and Salam spent a long time talking about this problem, and they came up with a proof of the Goldstone theorem, which they published together with Geoffrey Goldstone. And I will summarize it or paraphrase it. Firstly, the assumptions assume that there is a conserved current which generates a symmetry in the sense that the change in any field is given by the spatial integral of the commutator with the time component of the current, and assume that there is some field whose vacuum expectation value is not invariant, so this isn't zero, thus breaking the symmetry. Well then, it would seem clear that d mu j mu equals 0 should imply, in a relativistic theory at least, it should imply the existence of a conserved current operator, a conserved charge operator Q, the spatial integral of J0. And the broken symmetry condition is then that the vacuum expectation value, the commutator of phi with Q, isn't 0. And if you ask what intermediate states can appear in here, the answer is that if Q is indeed time independent, sorry, this thing keeps trying to switch itself off. If you want intermediate states in here, and if Q is time independent, I may have to do this manually. If Q is time independent, then the only intermediate states that can contribute there are states with zero energy, clearly. And if there are zero energy states, they can only come from massless particles. So that means there have to be massless scalar particles. They have to be scalar because they couple through scalars to the vacuum. So this was actually an impasse, because in a relativistic theory there seemed to be no escape from this. Spontaneous symmetry breaking implied the existence of zero mass spin zero bosons, and no such bosons were known, but if they had interactions of the sort of strength that was implied, they should have been easy to see. So, in that case, if there are no spin zero massless bosons, there can be no spontaneous symmetry breaking. On the other hand, if you just add in masses by hand, then you get these non-renormalizable theories with very undesirable properties. Weinberg commented on this, "Nothing will come of nothing, speak again," which is a quotation from King Lear, and expressed a sort of disappointment with which Salam and Weinberg finished up. They thought they'd disproved any possibility of this mechanism working. Well, of course, as you all know, physicists were in the end able to speak again. My own particular involvement in this, apart from having listened to the conversations of Salam and Weinberg, was when a young American postdoc arrived, Gerald Guralnik, in 1964. He had been a student of Walter Gilbert in Harvard, and Gilbert himself had been a student of Salam's in Cambridge. So he was a sort of grandson, in a sense. And it was natural that he should come to Imperial on his first postdoc. He had been working on this problem. In fact, Gilbert had suggested to him that he go and study the papers of Nambu. And he had been doing that and published some ideas about it. And when he arrived, we began collaborating together with another American visitor, Dick Hagen. And we, and of course others, found the solution. And as you all well know, the solution was the Higgs mechanism. This argument fails in the case of gauge theory. And I want to explore exactly why it fails in a minute. But that was pointed out by three groups of people. First of all, François Englert and Robert Brout from Brussels. Then Peter Higgs from Edinburgh. And finally, Guralnik, Hagen and myself at Imperial College. All three groups published papers in Physical Review Letters in the summer and autumn of 1964, which were incidentally chosen by Physical Review by Physical Review Letters for their 50th anniversary as among the most significant of that year. The simplest way to understand what's going on is indeed to think of what's generally called the abelian Higgs model, which is this model here, with it's just a gauged version of the Goldstone model. We have the same complex scalar field, has the same potential, but we now have a gauge field as well, A mu, and a covariant derivative for the phi. And if you do the same transformation as before, you set phi equal to a vacuum expectation value plus real and imaginary parts. It's useful to introduce another field B. B is related to A by a sort of gauge transformation involving the phi2 field. And therefore, F has the same form in terms of B as in terms of A. And if you expand, keeping only the quadratic terms, you can see that you have kinetic terms and mass terms for the phi1 field and the B field. So you've got a massive scalar field and a massive vector field. And so in some slightly mysterious way, the massless gauge and Goldstone bosons have combined to give us a massive gauge boson. Well, there's more to it than that. In particular, we have to look at the gauge problem, the gauge modes. The field equations, if you look at them, in particular the Maxwell equation, the d mu for f mu nu, are satisfied for any value of phi 2 at all, so long as B is a solution of the field equations, for example, 0. And that, of course, is just a statement of the gauge invariance of the original model. But if we want to know what A mu and phi were, and not just B, then we have to impose a gauge condition to fix them. And there are two different kinds of ways of doing that. If you choose the Coulomb gauge, dk equals 0, then B mu equals 0 clearly requires that phi 2 vanishes, or at least is a constant at most. On the other hand, if you choose the covariant Lorentz gauge condition, d mu a mu equals 0, that only requires that phi 2 satisfies the wave equation. So in that manifestly covariant gauge, actually the Goldstone theorem does apply. There is a field that is zero mass scalar, but phi 2 is a pure gauge mode. It actually has zero matrix elements between physical states. So how exactly has the Goldstone theorem been avoided in this? Well, the proof assumed that d mu j mu equals 0 implies the existence of a conserved charge operator. But that, of course, is only true if you can drop a surface integral at infinity. If you work out dq by dt, you can see that that is given by a surface integral of jk. Now, dropping that is perfectly legitimate in a relativistic theory, you would think, in a manifestly covariant theory, certainly, because what we're really interested in are always commutators, and in a Lorentz invariant theory, commutators, like Lorentz gauge quantum electrodynamics, commutators do vanish outside the light cone. So, indeed, there is, this is apparently a legitimate deduction, and it implies the Goldstone theorem. But it's not true in Coulomb gauge quantum electrodynamics, where the commutators actually vanish very slowly at infinity. They fall off, they do not vanish outside the light cone. When the symmetry is spontaneously broken, it turns out that this integral, Q, not only isn't time independent, it actually doesn't exist as a well-defined self-adjoint operator. For example, in the Higgs model, if you look at it, the leading order, Q is essentially the integral of B0, and that doesn't define a well-defined operator, it diverges. That's one of the things that was pointed out in our particular paper. And this fact, that this implies that distinct degenerate vacua actually belong to distinct orthogonal Hilbert spaces, which bear unitarily inequivalent representations of the commutation relations, is now seen as a defining property of spontaneous symmetry breaking. So that is how the Goldstone theorem was avoided. So how did this lead on to electroweak unification? Well, the first thing to say is that these three papers attracted almost no attention. They attracted a good deal of skepticism from some very eminent physicists, not least Werner Heisenberg. And by 1964, we knew about the mechanism, and we knew about Glashow's model, the SU2 cross U1 model, that could unify weakened electromagnetic interactions. And yet nobody put the two things together. That is perhaps a bit mysterious. I think it's one of the reasons is that the people who were thinking about the Higgs mechanism were still really thinking more about strong interactions than weak, although we were aware that there were problems for both. But it is rather mysterious, but anyway, there it is. I did some further work on the subject 3 years later, in 1967, looking in more detail into how the mechanism would apply to larger symmetry groups, non-abelian symmetry groups. In particular, how the pattern of symmetry breaking determines the numbers of massive and massless particles. And in the early part of that year, I had long discussions with Salam about this, which I think helped to renew his interest in the subject. Anyway, the model, the unified model, was finally written down by Steven Weinberg in 1967 in another famous Physrev letter. Salam presented essentially the same model in lectures he gave at Imperial College in the autumn of the summer or autumn of 1967. I should say I was not there because I was in the States at the time, but I've been told about these by, in particular by Robert Del Burgo, who was there. He didn't get round to publishing it until the following year. That again is perhaps slightly mysterious, but I think the main reason for that was that he was very busy at the time with developments of the International Center for Theoretical Physics in Trieste, which of course had been founded by him in 1964 and was in a rather critical period at this time. So what about what happened after that? A very important other development occurred in 1967, and that was the development of Feynman diagrams for gauge theories by Fadeev and Popov. That was a key advance. It's quite a difficult thing to do. Salam and Weinberg had both predicted that their theory would be renormalizable. They believed it to be renormalizable, but neither of them could prove it, nor for that matter could Fadeev and Popov. And it was finally proved in a real tour de force by a young student, Gerhard Toft, in 1971, a real tour de force relying heavily on the computer algebra program Kernship developed by his supervisor Tini Veltman. Then, of course, in 1973, the key prediction of the theory, the existence of the neutral current interactions, the ones mediated by Z0, was verified at CERN, and that led to the Nobel Prize for Glashow, Salam, and Weinberg in 1979. Stephen Ward was left out, arguably unfairly, because perhaps of this rule of three that is generally applied. Stephen Ward was not the prime mover of the work he did with Salam, I don't think, but he was a co-author of almost all the papers that Salam wrote on the subject, with just one or two exceptions. Toft and Veltman gained their Nobel Prizes they had to wait quite a long time, till 1999, to get theirs. And then, of course, in 1983, the W and Z particles were discovered at CERN. And in this period, that of course led to other Nobel Prizes, which I haven't written down here, for Rubia and van der Meer. During this whole period, in the 1970s and 80s, the gauge theory of strong interactions had also been developed as parallel. And that's a completely different kind of theory, quantum chromodynamics. So we now have, putting them together, the standard model, SU3 cross SU2 cross U1. Now, I haven't actually mentioned the Higgs boson yet. In 1964, or indeed 67, the boson was not really seen as a very important feature. It was a rather minor feature. It was actually it didn't feature at all in what Bright and Engler wrote. Peter Higgs did actually emphasize it. We mentioned it, but we failed to note that it would have a mass, although we were certainly well aware of the fact. It's quite obvious. The key point was always the mechanism, not the boson. The bosons are basically a triviality. But, of course, things changed. After 1983, or thereabouts, it started to assume tremendous importance, because it was the last remaining unverified piece of the standard model jigsaw, apart from the top quark. So it really had to be there, or something else doing the same job. And that inspired, in part at least, the two great collaborations, ATLAS and CMS. I'm very pleased to have a look at ATLAS this afternoon, and I'm going to look at CMS tomorrow. And these enormously impressive pieces of equipment have been designed, built, and operated over a 20-year period. And the result was the discovery of the Higgs in 2012, and Nobel Prizes for François Engler and Peter Higgs in 2013. So that really brings me to the end of my story. I would like to finish by saying I'm deeply indebted to two people who are sadly no longer with us. Abdus Salam, who was a real inspiration, a wonderfully stimulating person to work with or to be influenced by. That is incidentally me with him in an earlier incarnation. And the second one is my long-standing friend and collaborator, Jerry Guralnik, who very sadly died of a heart attack in April of this year. Thank you.
Thank you very much for this very interesting talk. I'm sure there are lots of questions or comments from the audience.
Very much interested to what happened in the 3 years between 64 and 67, in which you, François Engler, and also Peter Higgs, you agree that basically there was no major reaction to the papers. So did you fight for your... I'm curious to understand your feeling in those years.
Well, I certainly kept on working on the subject from time to time and giving talks about it and so on. Jerry Guralnik was actually discouraged from carrying on by his head of department, who said if you want to get a good job, you should find something else to work on. The other thing to say is that, quite surprisingly, I mean, Glasgow himself seemed to have forgotten about his model, and I don't think there was any sort of mention of it during that period. So it's a little bit of a mystery. But
are there any further questions or comments? Well, if not, then let's thank Sir Tom again.